Today we're going to discuss conservation of energy. To explain conservation of energy, we have to start by defining a couple of terms so that we can understand what we're talking about. When we say something is conserved, we mean it remains constant. So if you think about like if somebody tells you to hey, conserve your energy for the game tonight, they're not asking you to keep your energy constant. They're asking you to save some energy, right? So that's sort of the common use of the word conserved that we think of. So when we are talking about conservation of energy in science, we're talking about energy remaining constant.
Kind of like the whole thing of work.
Yes. This doesn't mean that the quantity can't change ever, but just that if we consider all of the forms that the energy can take, we will find that we always have the same amount of it.
Gotcha.
So a good example of this is if you have $1, that dollar can change forms, right? You could have 100 pennies, you could have 4 quarters, you could have however many nickels makes a dollar, you know?
Yeah.
But you still have $1. The amount of money you have hasn't changed, you've just changed its form. Now the example kind of breaks down because we spend money, right? Mm-hmm. And the amount of money we have does not remain constant. Mm-hmm. But in this example here, it can change to different types of currency, but you still have the same amount. You are familiar with the idea of conservation of mass. We've discussed this a little bit, that your mass doesn't change. Mm-hmm. Okay? If I take a block of wood and I cut it up into 1,000 little bitty pieces, when I weigh all of those little bitty pieces and any sawdust that I may have created during the process, I would find that the mass of all the pieces in the sawdust would be equal to the mass of the wood. Mm-hmm. By simply cutting it up, I haven't destroyed any of its mass. Okay? Energy is conserved in the same way. Very similarly. While energy is conserved, we need to discuss a specific type of energy for the concept that we are covering in class today. So the concept of conservation of energy applies to all types of energy. We're going to discuss one specific type today. Okay. So that's our second definition. We defined conservation. Mm-hmm. Now we're going to define a type of energy. And the type of energy that we're going to define is mechanical. Mechanical energy is the sum of kinetic energy and all forms of potential energy associated with an object or group of objects. This is a classification of energy. It's not its own unique type. So it's like an umbrella group under which potential energy and kinetic energy fit. If we were going to draw the sort of flow chart for it, we would say energy, right? And then we would have mechanical energy, underneath which we would have gravitational potential, elastic potential, and kinetic. All of those fit under the branch of mechanical energy, and then the other branch that we have would be non-mechanical energy. So anything that is not potential energy or kinetic energy is classified as non-mechanical energy. This would be things like thermal energy and radiant energy, like the energy that comes to you from the sun, right?
Gotcha.
All of those would be non-mechanical types of energy. Only potential and kinetic fall under mechanical.
Gotcha. So like chemical reactions and stuff like that would be non-mechanical?
Right. Chemical energy is a form of non-mechanical energy. Although some people would argue that chemical energy is stored energy and therefore could be classified as potential, but all types of energy other than kinetic and potential, like we said, classified as non-mechanical energy. Oh, you got that?
Yep.
Okay. Skedaddle on. Okay. In the absence of friction, so when we do what physicists do and pretend that things don't exist, when we ignore friction, total mechanical energy remains the same for a system. So that means the sum of all the kinetic and all the potential energies for a system stays the same if we ignore friction.
That makes sense.
This is what we call conservation of mechanical energy.
Because it stays constant.
Because it stays constant. It can be written as an equation, and that equation would be mechanical energy initial is equal to mechanical energy final. Pretty simple equation, right? If the only kind of potential energy we are learning about, or is in the system, I should say, is gravitational potential energy, then you can write the equation as 1/2 mass times velocity initial squared plus mass times gravity times height initial is equal to 1/2 mass times, I said velocity before, but it's actually speed final squared plus mass times gravity times height final. So you'll notice that these are just the combinations of the equations for initial kinetic energy and initial gravitational potential energy and final kinetic energy, final gravitational potential energy. So basically what they're saying is the total amount of potential energy and kinetic energy at the beginning should equal the total amount of potential energy and kinetic energy at the end. Now, you could start with lots of kinetic energy and very little potential and end with lots of potential and very little kinetic, right? But your total amount is the same if we ignore friction.
Friction just doesn't exist.
Just doesn't exist.
We're in space.
So here's a little example problem for you. A child is starting from rest and they zoom down a frictionless slide that has an initial height of 3.0 meters. What is the speed of the child at the bottom of the slide, assuming they have a mass of 25 kilograms? So it sounds like you got the correct answer. So do you want to talk us through how you did it?
So I first did the whole label what you have. So initial velocity is 0, the height is 3, and then the mass is 25. Height is 3 meters, mass is 25 kilograms. And then I started plugging in what I had from the equation that was previous. And since initial velocity is 0, then you automatically can cancel out the first part of the left side. But
Correct.
then also your final height is 0, so you cancel out the right part. So you're just doing the middle.
Yes, so what you're left with essentially is mass times gravity times height on one side, on the initial side, and then left with 1/2 mass times velocity squared. And so then what you should be able to do even is also cancel out your mass because it appears on both sides of the equation. And so then you can just plug in acceleration due to gravity, which is 9.81 meters per second squared, times the height, which is 3 meters. And then you can either divide by 1/2 or multiply by 2, however you want to go about that business. And you will be left with the velocity final squared all on its own. And then you can just square root it, bing, bang, boom, and you should come out with, as you did, 7.67 meters per second. Excellent. Just rocking it today. All right, so in some cases, acceleration isn't constant. We know this. We can see it in our everyday lives, which means that the kinematic equations that we learned in all the way back in chapter 1 don't function, because in order for kinematic equations to function, we assume acceleration is constant. But we know that that's not always the case. Even in the example there with the child going down the slide, their acceleration probably wasn't constant the whole way down, because there's other factors at play. However, since in these situations, even when acceleration isn't constant, we know that mechanical energy is conserved, we can use the initial mechanical energy and the final mechanical energy and then just skip the middle part, which is what we just did, which is really nice, right? We didn't need to use a kinematics equation to find her velocity at the end. We could use these equations that we just learned. It's very helpful for situations where you're just not sure if acceleration is constant or not. Very useful. Huh? In the event that friction is present, like in the world in general, mechanical energy is then not conserved. Friction causes mechanical energy to be converted into a non-mechanical form of energy. So, like heat, right? Thermal energy would be the energy, mechanical energy converted into a non-mechanical form. So, this doesn't mean that total energy isn't conserved, because total energy is always conserved. It just means that now it's not a mechanical form anymore. It goes in the other side of the umbrella.
So does that mean both the mechanical and non-mechanical is
Conserved?
conserved?
Yes. Total energy is always conserved. It just sometimes changes into a form that is more difficult to account for. So when you convert mechanical energy using friction, you convert it into thermal energy or heat, and you will often hear people saying that that energy is lost as heat. Lost gives the impression that we can no longer, like it's no longer there, but it is still there. It doesn't disappear. It's just in a form that's not easy to account or measure.
Got it. So it's just the whole fact of energy can't be destroyed, it's just transferred.
Yeah, changes forms.